Hello, my name is Sousa and I'm here to present our work entitled Damage Detection in Rotating Objects Using Position-Triggered Thermography. I am going to start with a brief introduction, then I'm going to talk about the experimental approach we use to detect damage in rotating objects, and afterwards I'm going to show you some results and compare them with static ones. I'm going to finish off with a few conclusions and possible future work. Online damage detection using non-destructive testing techniques is important to prevent damage in structures, especially in those with long operating times. If these structures make use of rotating parts and have minimal downtime, such as wind turbines, it becomes difficult to apply damage detection methods, mainly due to the constant motion of its components. Nonetheless, thermography can be used for this type of measurements, but there are some difficulties in field application that need to be overcome. A significant one resides in the necessity of properly aligning each image with the previous ones to obtain different thermograms with good quality. Therefore, the objectives of this work include detecting defects in rotating objects using thermography and comparing the obtained results with a static approach, while employing position-based triggering to align the thermographic images. Regarding our experimental approach, to obtain apparently still images of an object as it rotates, it is necessary to obtain a periodic signal that is strictly related to the rotation. This signal can have one or more pulses per revolution, as long as they always happen in the same angular positions. So, how do we do that? In this work, we created this periodic signal using a custom photodetector, which detects the difference between the blades and their background. This signal is then processed by the developed trigger controller, counting a predefined number of input pulses and generating the necessary output signals for the thermographic camera. A simple variant of thermography was employed in this work, where the specimen is first heated with a heat source, which in this case was a manually controlled incandescent lamp. Then, during the cooling phase, at least two images are obtained and then subtracted. The subtraction highlights slight differences between temperature distributions, where slower cooling regions can be indicative of embedded air pockets, that is to say, effects. As previously mentioned, in this work the necessary periodic signal was created using a custom photodetector that can distinguish the blades from their background. For this, a photodiode in photovoltaic mode was employed with high amplification. This is the basic schematic that we followed. As the expected currents were in the nanoampere range, the feedback resistor is in the hundreds of megaohm range, which is directly related to the necessary gain. Due to these very low currents and high gain, it was necessary to include protection against noise. This was created using an aluminium foil enclosure around the PCB. Due to the nature of this foil, it is not practical to solder a wire to it, thus it was connected to the PCB's ground plane using a screw plus a nut and jam nut pair. Okay. Since this foil is fragile, this was assembled inside a protective shell. Besides this, additional care was undertaken in maintaining potential noise sources outside of the main board, such as the voltage regulator. Due to the objective of this system, it is very advantageous to collect as much light as possible to have a larger signal. Thus, an adapter for F-mount lenses was included. Also, for mounting versatility, several options, metric and imperial, were also included. Here we can see the finalized version of this system. This is the trigger controller that we developed. The signal created by the photodetector is processed here. You can see that it is small and features an USB connection that is used for power, reconfiguration and logging. How does it work? The controller detects rising and falling edges on the input and counts them. Afterwards, when the count reaches a configurable value, it will trigger an output pulse. This pulse has configurable duration and delay. The latter is comprised of two main components, sync and phase. The first is responsible for synchronization of cameras between themselves and with the lighting. However, since we are only using a single camera in this work, it was not used. The second is responsible for the angular position of the object in the acquired images. That part of the delay is obtained using a configurable phase value and the latest speed measurement. The developed method was applied to damage detection in a carbon fiber blade from a 450 size RC helicopter. This is the final setup for both experiments, dynamic and static. It should be noted that the thermography camera expects low voltage TTL input pulses, which is to say 3.3 volt, but the trigger controller outputs a 5 volt TTL pulse. Thus, a conversion was necessary. In the static experiment, the RC helicopter was turned off and the blades were positioned manually in front of the camera. Then, the blade was heated using the previously shown lamp, and we acquired 600 images during the cooling phase. For this, we used an integration time of 419 microseconds and time-based triggering at 25 Hz. Thus, for this first experiment, the trigger controller and the photodetector were not used. This video shows the beginning of the cooling phase. In the dynamic experiment, the RC helicopter was turned on, rotating at 527 RPM. Once again, the blade was heated manually using the same lamp. In this case, we only obtained 60 images during the cooling phase, as the blade cooled significantly faster than in the static approach. The choice of integration time requires reconciling motion blur and the minimum temperature that the camera can see. In this situation, a value of 348 microseconds were used. The triggering signal was supplied by the trigger controller, resulting in approximately 10 frames per second. The video on the right shows the beginning of the cooling phase. For each situation, 2 images were selected for subtraction. Here, we can see the static result obtained by subtracting 2 images of the first video, and here we can see the dynamic one obtained by subtracting 2 images from the second video. The most noticeable defect is this one, which can be found in both analyses. There are 2 others that can also be seen in both, namely this one and this one. But it is also possible to see a region of concentrated heat, in black, that is in the middle of the blades in both situations. This will mask any possible defects in that area. For example, in the dynamic result, this defect does not appear, and it is probable that it is in the concentrated heat region. This is probably caused by the manual nature of the heating. In order to avoid this, it would be enough to wait more time to analyze that region, letting it cool down. But that would hide the other defects that are visible here. Thus, for complete analysis, it would be better to analyze multiple image subtractions. Along the top edge of the blade, both the defects and the concentrated heat region are not found in the dynamic approach. This is likely to be due to the very fast cooling of that region, as well as due to their relatively small size, which can be masked by motion blur. To conclude, the developed thermography-based method was used to detect potential defects in objects rotating at 527 RPM using position-based triggering. Reconciling motion blur and minimum temperatures can be difficult during the selection of integration time. This was the case with the used value of 348 microseconds, for which the camera already recommends temperatures above 30 degrees. The leading edge cools very quickly, and as such, the detection of defects in that region could require additional heat, smaller integration time, or longer analysis times. Since the defects in that region are small, the issue here could also be motion blur. In general, the obtained dynamic and static results are in agreement, and this approach also has a good feature for in situ measurements, in that all of the components can be placed in the same location. This is particularly interesting for a possible future work on wind turbines. For this, an approach like the one on the right will be sufficient. The whole setup can be assembled in the ground in front of the wind turbine, and the trigger system will be able to distinguish the wind turbine's blades from the background and trigger the thermography camera accordingly. In laboratory conditions, it is possible to use an artificial heat source. However, due to the sheer size of the wind turbine, this would be difficult to perform in fieldwork. Thus, it would be necessary to use naturally occurring temperature variations, such as the ones that happen around sunrise or sunset. Additionally, we would also like to compare the obtained results with other defect detection methods. Thank you, and if you have any question, feel free to ask.